Typing.
Okay, so good evening, everyone. Today we have Professor D. Indumathi going to talk on what are interaction cross sections and why do or why should we care about them. As you know, this is part of the ongoing online interactive lecture series, which are being organized for many weeks by the INO project. Uh, I think most of the people, at least today, who are online know Indu, of course, quite well. But nevertheless, let me take a minute to do my present duty of introducing the speaker. She did a PhD from Institute of Mathematical Sciences, Chennai. And then, of course, she worked in many institutes thereafter, both in India and abroad. And finally coming back to IMSc again, but as a faculty member. She's, of course, interested in the particle physics phenomenology, which tries to explain the observable universe in terms of appropriate theories or models to reach a better understanding of it. Uh, Besides, of course, she is, of course, one of the most active collaborator of the INO project, but also what is our interest is in the science education or science popularization and outreach, and in particular to the more younger children, especially to the school and college students, and also to the lay public, which is in fact usually very, very hard to kind of strike chord with. And she is in fact the head of the outreach effort of the INO project in this sense. So with those few words, now I request Indu to start today's lecture.
Thank you, Satya. Today's talk is supposedly extremely elementary. So I apologize to those who know the stuff. I also already mentioned that it will not do justice either to the experiment or to the theorists. I also have realized that I have forgotten to compile the version which had the list of references at the end. I will circulate that later. So that last page is missing, and I really apologize for that. That is really something that should not have happened. Okay. So let's start. So we want to talk about interaction cross sections, and really what I want to talk about here, I want to really give students a feeling for how we use cross sections and the value of cross sections. You know, what range of cross sections and what are their energy or angular dependence, to try to understand, first of all, how to build a detector, and second of all, having built it, how to analyze the data that we collect with it. So this is broadly what I want to communicate. And so it comprises two questions really, that why should we study cross sections in particular, and both theorists and experimentalists do study this. And of course, the other question, which is mainly aimed at uh, INO students, but also anyone who does either theory or experiment of such kinds, is why should we be interested in such a thing? And of course, because we are interested in neutrino cross sections, what can we reasonably expect to learn from studying neutrino cross sections? So, okay, I will start with some technical definitions for the cross section. So, since I promised you that it will be very elementary, I don't want you to be put off by the first technical definition. It's just, you know, because I talked about interaction cross section, so I must have at least one definition of it, which will be extremely elementary again. And I will then spend the first half of the lecture on elementary considerations. And then in between also, and also later, I will specialize to the case of neutrino cross sections, but I will come back actually to electromagnetic interactions quite often, because that's a very clean sample and a lot of things can be understood from there. And towards the end, maybe the last 5 or 10 minutes, I will leave you with some open questions on neutrino cross sections, because a lot is still unknown about neutrino cross sections. And recently, only people have understood this problem, and a lot of data has come out only in the last 5 or 10 years. And there is no satisfactory theory so far or phenomenology which actually fits all the data that is available from the various experiments. So I have no solutions to that. I will just leave you with that list of open questions towards the end, and that I think will constitute the most technical part of the lecture, which is still just graphs and figures. So it will be easy to actually appreciate what the problems are. And I will now start with that. What is a cross section? I hope that people can see the slides as they are being changed. So here is a definition of a cross section. Think of being hit on the head with a ball of cotton, or a football, or a cricket ball, or a coconut dropped from a tree. And I'm sure none of you needs to compute which will hurt you most, right? But in general, how do we, sorry, this should have been quantify. How do we quantify hurts and most? So what is that feeling of hurt? How do we quantify that feeling of being hurt, which is the interaction? And what is most, which is the largest cross section, right? That is what we really want to know. So some things are invariant. The speed with which the ball will hit you, that is its mass, its speed, therefore its momentum. This is what we call kinematics. This is independent of whether it's a football or a coconut, right? Or even if you have a large enough ball of cotton of the same mass, it's going to hit the same way, right? And that is called kinematics. So, some things depend on how hard the object is. What is the nature of the object? Basically, what I mean is, what is the nature of the interaction of the object with me? And this is what we call dynamics. So a combination of dynamics and kinematics both goes into understanding what a cross-section is. So we will first write the definition and then give examples of what constitutes what. So here is cross-section. Important to notice that it is a Lorentz invariant quantity. Therefore, it means that it can be computed in any frame. It's an invariant. It can be written in terms of Lorentz invariant variables. And its symbol is usually sigma. And it's given as the interaction with probability rate divided by the initial flux. So rate means, of course, probability per unit time. So what is this probability of interaction? This probability is the heart of the whole cross-section calculation, and this is what contains both the dynamics and the kinematics. So you can see that I'm not able to actually highlight in this because when I press my the mouse, it just goes to the next page. So you have to just look at it. So there are three sets of square brackets here. The first bracket is called the matrix element squared, and that contains the dynamics, which is the nature of the interaction, whether it is electromagnetic, strong, or weak. The second set of square brackets is a delta function of the 4 momentum, which includes the energy and the 3 momentum. So it is the energy momentum conservation, which is incorporated in the second square bracket. And the third one, which is the phase space, is actually related to the number of ways in which the initial momentum, P initial, can be distributed into the final states. So each one of them counts as an extra probability, and therefore it adds independently to the total probability. And so the cross section depends on, you can see the kinematics, which is the last 2 brackets, and the dynamics is contained in the matrix element square. So only that changes between interaction to interaction. Now, I'm not going to go beyond this. I'm not going to define initial flux. We're going to go very intuitively through all this, and we're not going to worry about equations anymore. We will instead go by examples. So what is the type of interaction that we are talking about? The classic interaction, for example, is AB goes to CD. Electron muon, elastic scattering. Electron proton, elastic scattering. Now, just to set some nomenclature, you can also have proton going to neutron. So that's the third equation. Electron proton goes to neutrino neutron. It is still an elastic scattering 2 going to 2 process, but the proton has become a neutron, so it's called a quasi-elastic scattering process. Now, if I have only one particle in the initial state, so there is no B, I have a decay process. For example, pi goes to mu nu mu. And in general, I don't need only 2 final states. I can have C, D, E, F, G. I can have multiple final states, but we don't really know how to deal with more than 2 particles in the initial state. The string theorists love to do this, but I will not go into that. So as far as we are concerned, either we have 2 particles or 1 particle in the initial state and any number of particles in the final state, and that gives us the kind of interaction which we want to capture using this notion of cross-section. I hope that is clear. Okay, so now we have defined what is a cross-section. This is the extent to which I'm defining it, by the way. And I'm telling you how these interactions are listed out in different ways and why are we actually interested in these cross-sections. So if we invert the expression for the cross-section, unfortunately, I don't want to go back to that equation, but you remember that it was a probability rate per initial flux, right? So if I want to know how many events are detected by any detector, then I multiply the cross-section back by the initial flux. And I, of course, multiply by the time because the cross-section was per unit time. So I have to multiply out by the total time over which data was taken. Okay. So this is how the theoretical expression, which is the cross-section, is going to be compared with the experimental quantity, which will be the events in any detector. So that is really the heart of the process. What you have to understand is that the flux, for example, I have shown in ICAL the initial flux. ICAL measures, for those who are not part of INO, I don't think there are any, but still let us define ICAL as an experiment where we study atmospheric neutrinos with some ion targets, and therefore the initial flux in ICAL will be the product of the flux of the atmospheric neutrinos falling on the detector times the number of targets in ICAL. So that's the initial flux. So this is a known quantity. The data taking time is also known to the experimentalist. So what happens is that if you ask the difference between the event rate and the cross section, the theorist likes the notion of a cross section because in some sense it is cross section per unit interaction per unit time, right? It's the number of events per unit interaction per unit time. Whereas the events depend on whether the flux can be larger or smaller, whether the targets are more, that means the size of the detector is small or big, or whether you've taken the data for a longer time or shorter time, all this will change the number of events. As far as the theorist is concerned, the underlying or the basic interaction, which is maybe, for example, one muon type neutrino interacting with something inside the ion in ICAL, that is the only thing that is of interest. Everything else can also always be multiplied out or divided out. And so the cross section is really at the heart of the theoretical understanding. Okay. So cross sections help in two ways. One, they estimate how big a detector you need to build to get reasonable number of events in reasonable amount of time. Now, this notion of reasonable is, of course, detector dependent and group dependent. I'm sure what neutrino people call reasonable is considered highly unreasonable by people in LHC. And well, let me not say people in LHC, people doing QCD studies in LHC, whereas people looking at rare events or beyond standard model events in LHC may still have not too much discrepancy between what is reasonable for neutrino events and what is reasonable for them. So everyone has their own definition of it. So there is an intuitive understanding of what that is, and that is how we will proceed. Is there a question? Okay. So,
You can go ahead, Indu, but
okay.
I have a question which I'll ask after the end of this.
No, no, no. If there is a question on that thing, please do ask. Okay.
Okay. The question is from Sadashiv. It says, does an interaction cross section be point care invariant?
No. See, the cross section is a Lorentz invariant. Okay. Now, this is something because, okay, maybe I should have gone, I didn't give a background to this. When we talk about, and what I will talk about in this talk, determining theoretically the cross section, is we are going to write this cross section down in a quantum field theory. A quantum field theory is a quantum theory which is consistent with relativistic quantum mechanics and also in addition has some symmetry group associated with it. That is my definition of a quantum field theory. So I have quantum mechanics, relativistic quantum mechanics, and some symmetry group. Now, all that I am talking about is only within that. So even though I talked about cotton ball hitting me and all that, I am not in the classical framework. I am only in the not only quantum mechanical but in the quantum field theoretical framework. Okay, it is best to identify like that because many of the inputs that we use, so for example, CPT and all that, arise only from this kind of locality, notions of locality, which this quantum field theory have, and things like that. So let me restrict myself since the question has come. I am actually talking about a quantum field theory in which I am actually computing these cross sections. I hope that is clear. Okay. So there are many other things that once you relax many things or look at other ways of looking at things, you can have many other solutions. But I am not going there. Okay. Fine. So one is the cross section. First, cross section helps you to estimate how big a detector you need to build, so that you have some number of events. If it's too small, you'll have to wait too long. If it is too big, then you probably have spent too much money building it, and so on. So that estimate is very important. So even before you build a detector, the cross sectional estimates will tell you how big a detector you need to build. Next, it also helps you to analyze the data to estimate the unknowns. For example, people in ICAL want to look at neutrino oscillation parameters, and you fit the theory to the data, and the theory will include a knowledge of the cross sections. And you have to put that in to analyze the data and then fit your unknown parameters using that. So cross sections help in the beginning and in the end, right? So they are there in both places. And very often, this is especially to INO students who are doing detector simulations, very important to know what you have put in and what you have got out, because the more information you put in, the more information you can get out, but it doesn't mean that the experiment will actually give you that information. You may just be putting in too many parameters and you think that you've got nice answers out of it. It's a very, very tricky thing sometimes to make sure that you've done your theoretical simulations properly. Okay. Now, we only talked about something called sigma as a cross section. However, sigma is actually not a well-defined quantity because it's actually a differential variable. It's a function of many things. And typically, and all that I'm interested in this talk is the function of energy and scattering angle of one of the particles in the final state. And very often what is overlooked is that it's also a function of the available initial energy. So these are the three things that we will be looking at in the rest of the talk, that the cross section is differential in the energy of the final state particle. One of them, let us say, the scattering angle of the final state particle, and also depends on how much initial energy is available in the process. These are the three main parameters that we will be looking at. Now, here is an aside for ICAL. Because of this, we can refine the question of cross sections further. For example, what should be the angular resolution of the detector? Because we know that cross section is angle dependent. So if we want to look at this angular dependence, then we must have a suitable angular resolution of the detector. Also, what range of energy should this detector be sensitive to so that it can do the best physics studies? And here I have a question for especially the ICAL students. Do you know what energy and angle of muons ICAL is most sensitive to and why? I'm going to pause and ask, or maybe I read out the three questions. Does this energy and angle correspond to peak of energy of atmospheric neutrino fluxes? The answer is clearly no, because the third question was no, then why was this chosen? So anybody, let me give a pause of 1 minute for people to answer these three questions. You can answer it in any order.
Okay. Also, I mean, if the participants are there on YouTube, you could also kind of briefly
Okay.
type because you have no way to directly answer them. But
Okay. Okay. You
on the
please write
Zoom, of
to.
course, on the Zoom, there you can raise your hand and I
Yeah.
will
Yeah. Yeah.
allow you to answer. Yeah, there are quite a few students at the
Okay.
moment.
Okay. Pick one and let them answer. Pick three so that they can answer three of them. I mean, see, you must understand. I am talking to my computer. I don't see any of you. It's extremely hard for me because I always look at people nodding and to make sure that I am going at the right pace and people are understanding. And all I have is this computer in front of me, literally, So I need some feedback to know that someone is listening. Okay, so what energy and angle? Does anyone know?
No, there are no raised hands, so I'm
Okay,
afraid
fine.
I will not be
Okay,
able to.
good. Then the question for the audience becomes a homework for the INO students, especially the
Wait.
ICAL
So
students.
there is a raised hand, but
Okay.
not a young student, but she is
Oh,
quite a senior researcher now, I can say. Okay, let me go ahead.
I mean, am I eligible to answer this question because
no,
this is really
no,
for
no, no,
students?
no, no, no. You are not allowed to answer this question. Sorry, no. Okay, but yes. So I think it is important. So again, I want to reiterate, when we are doing these simulations, we very often forget these kinds of things. Why did we choose some centimeters of iron plate? Why did we choose so many layers? Why did we choose certain mass of detector? Okay, so I will tell you in short. So I want you to go back and think about it. So we know that the peak of the energy of atmospheric neutrinos, maybe you don't know, is around quarter of a GeV. Okay, around 250 MeV. Okay, but our ICAL is sensitive to few GeVs of energy. Okay, and it's more sensitive to around 5 to 7 GeV, and of course vertical direction more than horizontal direction. And the reason is that the resonance effects, the matter dependent MSW resonance, and therefore the hierarchy between that is the mass hierarchy between the 1, 2, and 3 type of neutrinos, that is in the mass eigenstates. All this is more sensitive in the few GeV, 5 to 7 to 9 GeV of muon energy. Okay, and it is, for the case of muons, it is more sensitive in the up versus down direction. That is why you want to be sensitive to vertical direction of muons, and you want to be sensitive to few GeV energy, because that is where the matter effects are most enhanced. And that matter effect, the difference between the matter effects on neutrinos and antineutrinos, is what gives you the hierarchy dependence, which is really the core question that ICAL has been mooted to answer. Okay, does this answer the question? So the reason it was chosen, even though it doesn't correspond to the peak of the energy, we are not going to get the maximum possible events at ICAL, but we choose it because that gives you maximum sensitivity to the physics that we want to study. Of course, for the advanced students, I was hoping somebody will answer this question. There is an additional complication of the magnetic field being in the y direction for ICAL, with apologies to all those who don't know the ICAL geometry, that because of that, in fact, there is also a phi dependence, and therefore it is not symmetric in phi. There is a theta and phi dependence because of the presence of the magnetic field. So this is the kind of questions that you want to answer, and this becomes important when you have to go back and ask the question, how does the cross section change depending on the energy and the angle, right? And therefore you see how one feeds back into the other, and this is kind of a chicken and the egg. You have to keep on refining it by asking the input question and then arranging for the output to be as sensitive as possible to the input question that you have. Okay.
Okay.
So yeah, please.
I have a couple of things. Okay, now the screen, I had some issue. Now it got cleared when you went to the next screen, next slide.
Okay.
But two questions or maybe answers to your questions. One is here by Hariom. Maybe he can answer. He can now speak.
Sure. Please, very happy. By the way, I don't even know the new students, so I'll be very happy to hear from them.
Yeah.
Okay?
Hariom.
Sir, this ma'am, this first question, this energy of muons in this ICAL. So this is the atmospheric muon or this muon generated by this neutrino iron nucleus?
It doesn't matter. However the muon comes in, right? It doesn't matter whether you can put it through your electron gun, you can get it from the atmosphere, you can get it from neutrino interaction in the ICAL. But the detector itself has a certain sensitivity. It is not sensitive to all energies and all angles, right?
Okay.
For example, muon coming in very horizontal direction, it will hardly go through 2 or 3 ion plates. You're not going to reconstruct that very well. So you can already see that vertical muons will reconstruct much better than horizontal muons in ICAL. Also, you must understand one thing. There is something very important in theory that we talk about. However I produce a muon, as I said, there were 3 examples that I gave. There are many more, in fact. I can produce a muon from your a giant gun. I can produce a muon from cosmic ray flux, that is direct cosmic ray muon flux. I can produce it from a neutrino interaction inside the detector. I can have it produced in the rock outside the detector, and the muon enters the detector. Whatever is the initial process that produced the muon, the detection of the muon is independent of that process. It goes by a very important name called factorization theorem in theory. Okay, so we don't care how it is produced. Once a muon of some, say, 5 GeV at an angle of, say, 20 degrees is produced, then the way it interacts with the detector is the same. Is this clear?
Ma'am, I just want to ask this sensitivity of this energy, because we are taking this curvature from the curvature of the muon.
Correct.
So is this depend on this strip width we are taking, like 3 centimeters?
Those are even finer details. See, this is. I mean, I'm assuming that mostly INO people are here. Okay, but I am not going too much into the details because I have not defined ICAL. But you are right. There is a complication of strip width. Right. There is a complication of the air gap. There is a complication of even ion plate thickness, magnetic field. Everything, every detail will go into this, and every detail has to be studied before you decide what is the answer to this question. It's just that a lot of this is known. All your senior students have already done this analysis. Please go and read their papers. A lot of this is available in their thesis. This is what a lot of thesis contains, right?
Yes, sir.
It's important. So, for example, you should know that if I have a vertical muon in ICAL, then when we know that muon is minimum ionizing particle, so when it goes through one layer of 5.6 centimeters of iron, typically about 80 MeV of energy is dumped in it, right? So it's 80 MeV per layer. So you can immediately see that 150 layers means beyond 15 GeV, you will not get any detection of muon momentum if you did not have magnetic field. If it just goes in a straight line, right? Maybe you can add a root 2 or a root 3 factor if it's going at an angle, right? Because then it will have slightly longer length. But this gives you roughly the idea of what is the kind of, round number estimate of what is the kind of energy that you are going to be sensitive to. You can do this estimate for even super K, for example. You can do it for SK. You can do it. You can do it for Dune. You can do it for any experiment. You should always be able to get a 0th order result, depending on very coarse characteristics of the detector. Then it will tell you why it is that they've built the detector in that way.
Okay.
Okay.
Okay, thank you.
Very good. I hope that is clear. And also you have understood that it does not correspond to the peak of the energy, but it is where the matter effects are most, which is why it is made for that, right?
Okay.
Okay. So now we have even simpler questions. Okay. I don't even want to look at very detailed, energy dependence of this, but I want to ask ab initio itself. How do I know what cross section is relevant? This is why I call a qualitative approach. So let me give you a little maybe motivation or background. All of you would have studied the solar neutrino puzzle, right? You know that Kamioka, Super Kamioka, and then even the snow experiment, all of them looked at elastic scattering of neutrinos, the solar neutrinos on electron, right? Now, why is it that they did not look at scattering of the nucleus? Or if you have iron, then why didn't they look at it through iron? So that is where we ask the question ab initio itself, what kind of processes do you expect will actually contribute the maximum given a certain flux of initial particles, given a certain type of neutrino, whether it comes from the sun, whether it comes from the atmosphere or anything else. Oh, I forgot to add a graph which tells you what are the sources of neutrinos, but I guess all of you know that. So the question is, how do we understand the relevance of a cross-section? So how do we understand quantum mechanically what is the size of an electron? Because we think of electron as a point particle, right? So the best thing to look at is to look at the de Broglie wavelength, h by p. H I write is 2 pi h cross, and I multiply and divide by a c. And we know that h cross c is 200 MeV Fermi. I hope every particle physicist knows that h cross c is 200 MeV Fermi. Okay. Now I'm asking the question, if the energy of the electron is 300 MeV, and what is the mass of the electron? About half an MeV. So gamma of this particle is about 600. So it's extremely relativistic. So if you look in the brackets below the equation, Pc is equal to E because P is mv gamma and V is of the order of C. So the denominator I can simply substitute as 300 MeV. So I get lambda as about a few Fermi, 2 pi Fermi essentially. Okay. Physically, what does this mean? Lambda actually reflects the size of the electron. What does the de Broglie wavelength tell you? It's where the wave function has maximum probability of finding the electron, right? So the size of the electron is a few Fermi, and it is closest in size to that of the nucleus or the nucleon itself, which is also few Fermi in size. And that is why the name cross-section is given. Cross-section is actually has a dimension physically of area. Cross-section is in meters squared. So it's effectively like a geometric cross-section. So what it's telling you is that the electron is of the size few Fermi because that's the corresponding wavelength, and therefore it likes to see meaning it likes to interact with something which is of similar size, which means that a 300 MeV electron is going to more or less interact with a nucleus or a nucleon, which is a few Fermi in size. If you go from 300 MeV to few GeV, then lambda becomes much larger, or lambda becomes much smaller, which means that the particle it is most likely to interact with is much smaller than a nucleon size, and therefore it is more likely to interact with the quark or gluon constituents inside the nucleon. So as the energy increases, it's going to interact with the sub particles which are inside the proton or nucleon, which are the quarks and gluons. However, if it has less energy than 300 MeV, then its wavelength becomes larger and larger. It becomes closer to 1 angstrom, and therefore it becomes more of atomic sizes. It is more likely to interact with the electron in the target atom. I hope this is clear. This is actually the crux of all cross sections. So if you have a low energy probe, which is an electron in this case, it will interact with the electron in the atom. If you have a higher energy probe, it will interact with either the nucleus itself or the nucleons inside the nucleus. And as you go to higher and higher energy, it will interact with the constituents of the nucleons, which are the quarks and gluons. So how do you decide? And that is the example that I have in the next page. So this is the summary of what I have said. The cross-section is largest when the wavelength of the probe matches the size of the target. So as the energy of the electron changes from keV to meV to GeV, it interacts respectively with electron, nucleon, and quarks inside the target atoms. Okay, and the same occurs with neutrinos as well. And when I say give examples, I hope that the audience is going to give me the examples. So I will simply list them all, and I will expect the audience to give me examples. So let's start with lower energy. Energy of the neutrino is much less than 1 GeV. So now you can see that I have gone from electron probe to neutrino probe. And these are simply examples. I've just chosen them at random. So for example, I have nu mu electron goes to nu mu electron, okay, which is called neutral current. However, if I have nu e electron, then I can have nu e electron goes to electron nu e through either charge current or neutral current interactions. Okay. Similarly, if I have instead of the electron in the atom, if I have a proton in the atom, then when nu L goes to nu L, I have a neutral current. And when nu L, L being the lepton, goes to the lepton, charged lepton, neutron goes to proton, I have a charge current interaction. And you know why it's called quasi-elastic, because N goes to P, but it's still an elastic scattering process. So all these interactions, and in fact, the second line is of interest to the ICAL people, because it's on protons, which are contained, or the neutrons, which are contained inside the ion. So at few GeV, you expect to see quasi-elastic scattering. Now, let us look at the second example, nu E goes to nu E. Where is this seen? I hope all of you realize this is the solar neutrino interaction, right? And the first one, nu mu E goes to nu mu E, is also the solar neutrino interaction. And since the solar neutrinos are of the order of 10 MeV, this is the most dominant interaction for solar neutrinos, and you are not going to see anything like scattering on the nucleus or nucleon or constituents of the nucleon. There is simply not enough energy. Okay. Now let's go to the second case where the neutrino energy is of the order of few GeV. So what did we see here? Few GeV means that it's of the order of Fermi or less, but not too small. So which means that either the proton goes to excited state proton, or neutron goes to delta plus, or so many other processes, resonance processes are possible. So it produces excitations in the final state, and these are called resonance processes. Okay. And in fact, these are the most complicated to calculate. I will show you one example of resonance processes later. Okay. And when the neutrino energy is much more than a few GeV, you have what is called deep inelastic scattering, where the entire initial state nucleon, which is proton, simply breaks up into X, where X can be any number of hadrons, small h being a number of hadrons. And what happens is that the proton, which may be bound or free inside the nucleon, actually the energy of the neutrino is so large that it's actually seeing the substructure, which are the quarks and gluons inside the proton, and interacting with them. And that's why it results in breaking up of the entire nucleon itself. When the neutrino remains a neutrino, I get a neutral current process. When it converts into its charged lepton partner, it becomes a charge current process. And typically in such interactions, this X is not seen. This bunch of hadrons is not seen. Only the final state lepton is seen in the process. So we have seen quasi-elastic scattering, resonance scattering, deep inelastic scattering, and these are the three main kinds of interactions that we will see in ICAL as well. And in the very last slide, I will have a remark to make on this. So I hope that this is clear.
Indu,
So this,
there are
yes.
a few questions.
Okay.
First, I'll take a couple of questions from students and then come to one question from Professor Datar. Okay, one question from Raj. Actually, it probably corresponds to your earlier, the questions that you posed. He says energies in GeV and angle would be opening angle of the detector. I think this is a slightly delayed reply that I'm giving you. I think this is he's trying to answer your three questions that you asked in the
right. Okay.
Okay, if you want, you can make a comment about it, but I'm going to the question now, one more question from another INS student. It says, let us say ICAL detects neutrino events, then the energy of muon plus hadrons equal to neutrino energy. ICAL is good enough for muon, but uncertainty is high for hadrons.
Yeah.
Then how do we deal with it?
Okay. Okay. It's a very specific question.
Yeah.
The first one, I have no more comments on, except that when you say opening angle, yes, we should be a little careful about opening angle. Maybe I should actually make a remark over here, because some people have asked me. I was hoping my student will be in this talk, but he is not here. He had asked me this question last time. See, opening angle is actually not a Lorentz invariant quantity. Angle is not a Lorentz invariant. The corresponding quantity, which is Lorentz invariant, is called rapidity. Okay, so when you go from frame to frame, rapidity adds, but angle can go in very different ways. Okay, so when you say opening angle, it means you have decided on a frame. Within that frame, what you say is completely correct. But I just want you to remember this fact. So, for example, you have thought of a process in which, say, you have a target and a beam hitting it, and then there's an opening angle of final states. Perfectly all right. But if somebody changes it to, say, beam on beam processes, this opening angle can be a completely different quantity. So otherwise, the answer is perfectly correct. Okay, that is point number one. Point number two was about this hadron energy is not very high. So if you see, I'm not sure whether who asked the question, some first year student or
yeah.
Okay.
This is second year student Sadasi.
Okay, but yeah, so maybe he's not very familiar with these kinds of calculations. So if you look at what is actually simulated in ICAL simulations, you do not ever look at the original energy of the neutrino. What you actually plot against is the energy of the muon, and an additional variable, if you want to have, is the energy of the whole hadron bunch. But that is very, very coarsely binned, because as you pointed out, we don't know it very well. We can't determine it very well. So what you really are pinning your hopes on are the muon energy and angle, and nothing to do with the hadrons, except in a very limited fashion. Now, I mentioned to you that the cross-section is differential in the energy, the angle, in fact, in the initial energy, everything, right? So it depends on all the quantities. So when you say that you don't want to use the neutrino energy, it just means that I don't want to actually use a process where I'm asking what are the events, total number of events, because that depends on the total cross-section, because the total cross-section depends on the neutrino energy. What you're asking for is the events as a function of angle, events as a function of muon energy, where actually I can forget about the neutrino energy, not fully, but approximately. And within that, because of some scaling dependencies, which I don't want to go into, within that I can ask what is the dependence on the muon momentum or muon direction. Okay, so there have been some studies where we try to reconstruct the original neutrino energy and direction, but as you point out, it will be quite poor. Okay, so that is why, in fact, you have to be careful about what variables you choose. You must make a choice of variables that will be maximally sensitive to the quantity that you're trying to measure.
Okay.
Yeah.
So,
for example, if you want to look at L by E oscillation, the neutrino oscillation is an L by E of the neutrino. But what will happen is that because your L and E of the neutrino, L depends on the theta and E depends, of course, on the E. And therefore, if you don't have good direction and energy reconstruction of the original neutrino, you're going to get a very poor L by E curve. So you never look at L by E. That is why we never look at L by E. We look at the theta dependence of the muon. And so you will not see an L by E plot really in the INO white paper. Please go and take a look, okay? That's why you don't do it. Is that clear?
Indu, also maybe a question or clarification from Professor Datta.
Yes.
Can you hear me?
Yeah, sure.
Okay, so this is basically just a comment for the cross sections below GV and probably in the MEV region, QMEV to higher. So there actually the charge current cross section on the nucleon is much higher than the neutral current cross section in the electron. Of course, neutral current plus charge current. If you include both of these amplitudes and compute the cross section, it still is much smaller than the charge current cross section of the nucleon. However, of course, there are advantages in looking at the nu E cross section. And for instance, Super K has looked at them, given directionality, where you can say that the neutrinos actually come from the sun and so on. The other part is that if you want to detect through the charge current, then the nu EP, which gives you a neutron in the final state, unless you detect that, your background doesn't
Yes.
really decrease. So the cross section is high, but
Yes.
it's more difficult to
Yes.
detect. In
Actually,
fact, that goes even for the deuteron, the
Yes.
nu E going to
Yes.
plus
Yes.
deuteron. So okay,
Yes.
the cross
I
section may
hope
be
the
large, but
students are
sometimes it may
listening.
be
No.
not
Yeah,
the
correct.
best thing to look at.
Yeah, correct. So in fact, I hope students are listening. These are very important caveats. So these are all very generic kind of statements that I'm making. There are many exceptions to this. In fact, one very famous exception is nu E bar P goes to E plus N, which is very, very special because the energy dependence, which I will come to soon, is E squared rather than E. So it's really huge. Okay, so there are many things actually, and that is that actions being left-handed. Okay, so I will not talk about that here, but when you come across some things which are anomalous, you must please ask yourself why and try to understand it. Okay, so these are all caveats. So what statements I'm making are very generic because I made it on the basis of simply some wavelength considerations, which is very, very crude estimates. Okay, but you have to sit and refine it and of course compute the cross sections. And in fact, I think I'm almost through with talking about the different kinds of cross sections. I will be actually showing you a lot of graphs from now on. Okay, so we can try to appreciate what that looks like. Okay, so I think I have finished with everything on this. Yeah, quasi-elastic, resonance, and deep elastic. So I will proceed now. Thanks, Vivek. Yeah. Okay, so now I just want to make two statements because I'm not going into very much detail about energy and angle dependence of cross sections. Very briefly, actually, as I keep telling you, so I wanted to show you at least once. You can see the equation on this page. I have written the differential equation, the differential expression for cross section as a function of the final state electron energy, DEE, and the final state angle, electron angle, cos theta. And so let's take two examples. Let's go back, not to the equation, but go back to the first point. Let us look at the solar neutrinos being detected at Super K. Super K is a water detector. And in fact, as Vivek pointed out, this process is used because nu E goes to nu E is isotropic in the center of mass frame. Again, this is due to weak interactions being left-handed. But when you boost this to the lab frame, what do you mean by boost it to a lab frame? Because you know that the electrons in your Super K are at rest. These electrons are the ones which are attached to the molecules of water. So they're the electrons belonging to H and O. And the neutrino is coming from outside, and so that's called the lab frame. And when you boost it to the lab frame, this cross-section gets forward peaked so that the scattered electron points back to the sun. So it's a very nice reason to use this, apart from, of course, the energy being enough to give you Cherenkov radiation so that you can get a nice forward peak. And therefore, you can use this direction dependence of the cross-section to make sure that these are actually solar neutrinos. So that's the importance of knowing the angular dependence. Another example is any deep elastic scattering is forward peaked. And here we come back to that equation that I showed you. D sigma by DEE d cos theta goes as 1 by sine to the power of 4 theta by 2. And you can see that it is extremely forward peaked. And this angular dependence can be used to separate out different kinds of interactions in the same detector. So different interactions have different angular distributions, and you can fit the data to different angular distributions so that you can actually pick out the strengths of different interactions and use one data set to actually try and fit many cross sections at the same time. So this is about angle dependence. Now, when I come to energy dependence, I actually want to go back a little. I want to go and look at all possible interactions starting with QED because it's very important to look at this energy dependence. So I'll start with the classic case. I think I should be finished on that. I'll start with the classic case of electron positron goes to mu plus mu minus, and the cross section. Don't worry about what it is. See that in the denominator it has S, and in the numerator this is charge power 4, and charge power 4 I've written in the bottom equation as alpha square. So alpha is the coupling constant, 1 by 137, which characterizes electromagnetic interactions. And what I really want to highlight is this S. S is the total square incoming energy. So it's the sum of the forward momentum of the electron and positron squared. And in the center of mass of electron and positron, which is what happens at many E plus E minus detectors, it is actually proportional to the energy squared. And so you can see in the graph alongside that it decreases with the initial energy. Root S is simply proportional to the energy E. And you can see this very nice fit, very old data. Those who know what Jade, Mark, and Pluto are will appreciate that this is a really nice whole plot. Okay, this we can ask what happens at other energies, and this is what happens at other energies. So 10 to 40 GeV is what the previous figure showed you. Now I'm actually plotting the cross section for all energies from a fraction of a GeV to about 200 GeV. And you can see this is the only example I have given of resonances. You can see that wherever there is a matching between the incoming available energy, which is root S, and the mass of the final state particle, if there's a single particle which can be produced. For example, E plus E minus going to Z happens at 91.2 GeV because that's the mass of the Z. There is a huge enhancement in the cross section. And similarly at omega, rho, phi, j psi, and other such resonances. So resonances are exactly what they mean. There's a resonance enhancement of the cross sections at these values. But otherwise, you can see that for electromagnetic scattering, the cross section simply decreases as 1 by S. And therefore, you can see that this is a log plot. That's why when you see almost a straight line as a 1 by root S. And this is something which is a very important consideration, which is actually seen in all QED processes. Now, question, is it the same behavior for all processes? Now I have written, you can see everything looks the same. I have three equations. The first one is for E mu scattering to E mu, elastic scattering. Second one is EP goes to EP, elastic scattering. Third one is EP goes to EX, deep elastic scattering. But the main thing is they're all QED, alpha squared processes. And they all have S or E squared in the denominator. They all show the same dependence, but whatever is in the square bracket, those dots are all different for each other. But the overall energy and angle dependence are very similar to each other. This very important decrease of the cross-section, which I've put in blue with the initial energy, is a consequence of what is formally called the unitarity of this matrix. Basically, it says physical cross-sections must be finite. So it's very important that the cross-section decreases with energy. Now we come to weak interactions. In weak interactions, you can see that you don't have this 1 by energy squared dependence because you have a coupling constant. Instead of alpha squared, you have what is the Fermi coupling constant, and the Fermi coupling constant has dimensions of mass to the power of -2, GeV power -2. So first of all, it's very small, 10 power -5 in units of the nucleon mass, but also it has an energy dependence so that the combination GF squared S has the same dimension as 1 by S, and therefore it looks like the energy dependence is in the numerator rather than the denominator. And so in the lab frame, if you do the deep elastic scattering experiments, it looks as though the cross-section is going to keep increasing as E. And this, in fact, cannot happen if you believe in the unitarity of the S matrix, because then the cross-section keeps on increasing with energy. But this is a reflection of the fact that Fermi's theory is an effective theory, and the coupling can and does get modified with energy. I will not go further than that, but please keep this in mind. At the energies that are relevant to ICAL, cross-section is indeed increasing for weak interactions with energy, but this cannot go on forever and will get modified because the coupling constant GF will get replaced by the proper theory coupling constant, which is G weak, and then many other things will come into play, especially renormalization. So I will not make any more statements than that. So here is the cross-section for deep elastic scattering from NewTEP data of, you can see from 50 to 350 GeV, and you can see that it's linearly dependent on E because what is plotted is sigma by E, and it is practically a straight line for both nu and nu bar. And this very famous factor of roughly 1/3 comes from actually the it comes from the weak interaction couplings actually for the two. Anti-neutrino cross-section is always a factor of 2.5 to 3 smaller than neutrino cross-section. But you can see that the cross-section is increasing with E. For all purposes at ICAL, you can assume that the cross-section increases linearly with the neutrino energy. So now I have a whole bunch of details. So we are now going in, this is my overview talk about cross-sections, why they are important. And now I will show you some details, especially with respect to neutrino interactions. First thing is the total mess that you see. Look at the big graph on the right-hand side. Total cross-section for the charge current interaction, again divided by E nu, because now we know that it's linearly dependent on the energy. So you can see it's practically a straight line. And you can see that all on the right-hand side are dates like 79, 81, 82, 97. And only now you can see that in the 2000s, there's no data in between at all. Suddenly everybody woke up to the fact that cross sections are not very well known. So NewTev, Mini-Boon, Minerva, T2K are all now taking data on neutrino cross sections. These are not very well known. And the left-hand side is an old plot. You can see that the data really doesn't fit the solid line because simply there are too many discrepancies, and I will show that actually in the next two plots as well. So the first thing is a total charge current neutrino cross section on carbon 12 from Mini-Boon data, and you can see that all the colored lines, beautifully colored, don't go through the data at all.
Indu, can I disturb again?
Sure. Yeah, sure.
On the YouTube by the same students. So that for atmospheric neutrino, those
Where should I go back to which slide? I'll go back to previous slide. Yeah, okay.
Those passing through Earth matter, electron neutrino can undergo inverse muon decay with electron and release muon energy at E greater than 11 GeV. How ICAL can differentiate from actual atmospheric neutrino, atmospheric muon neutrino?
Sorry. What was the first part of it? What can give you that?
For atmospheric neutrino, those passing through Earth matter.
Oh, yeah. See, I mean, by the way, you don't need to do any inverse beta. Every deep elastic scattering with the rock also gives you muons, right? So all of them will be there. By the way, there's another thing. Because nu tau is also massless. There is a lot of nu tau coming from below. And nu tau gives you tau, which can also decay to mu. I mean, many things can happen. And mu tau can go to tau, which can then decay, which will give you nu mu. And the nu mu can again interact with the rock to give you mu. Many things can happen, okay? The main thing to realize is that all these are coming from below. Because it so happens, we are very lucky that the neutrino oscillation wavelength for these GeV kind of neutrinos is such that neutrinos coming from above are hardly going to be affected. You need to have at least 400, 500 kilometers length to see any effect of oscillations. And that only happens if you're at least in the horizontal direction or, coming from below. So if you look at the difference between above and below, there are two things. One is that the neutrinos which are interacting inside the detector will have vertices inside the detector. So you can try to find that vertex because the muon starts inside the detector. Whereas the neutrinos which are coming, the muons which are coming from outside mostly are coming from below. So they're coming towards above from below, and they will not have vertices inside the detector because they will come into the detector from outside, and so you will start seeing the track from the first bottom layer itself. So these are the two things ways in which you can actually distinguish these kinds of events. Does that answer the question?
Also one question from Bala on the Zoom. So he can ask the question.
Oh, by the way, I just saw one thing from Vivek saying center of momentum is a better thing to say than center of mass. He's absolutely right. We're just ancient. We just talk of center of mass, but it's actually center of momentum. Okay. P and minus P are the momenta with which the two particles collide, and that is the center of momentum frame and not the center of mass frame. Yeah. Thank you.
Bala, can you
ask the question?
Yeah.
Hello.
Yeah, please go ahead.
Ma'am, the previous slide, I mean, for new TeV.
Sorry,
this is I mean, sigma versus E. There were some those yellow regions. What
from
those?
NewTev, yeah.
I mean, those yellow regions, yellow bounds. What do they say?
Oh, those are the systematic errors. The yellow things are the systematic errors.
Okay. Yes, ma'am. Thank you.
Sorry, yeah, I haven't. As I said, this talk neither deals with the theory nor with the experiments at any great length. I'm really sorry about that. Just a generic overview, okay? And I'm sorry, I seem to have gone over time. So anyway,
no. Don't worry. There are questions in between. So
yeah. So one thing to understand is that there is a deviation from the 1 by E or the proportional to E behavior at low energies. So we are interested in looking at the low energies, we meaning theorists, because ICAL anyway is not going to see anything unless you're at least at 5. Okay. And again, you can see this factor of 2.5 between the neutrino and anti-neutrino cross sections. Okay. That's it about this. Now I want to go to some more modern data. I'm really sorry that that page is left out. So this is from a very nice review. It's a kind of 100+ page review by Martini et al., which is the last name on this. Okay. And you can see that first the theory doesn't fit at all. Of course, Martini's Fit agrees, which is why he wrote the paper. But most of the earlier calculations, RFG's, the relativistic Fermi gas, very far away, and even the random phase approximation of Sajjad is very far away. So many of these questions have come. So what it turns out is that what Martini tries to tell you is that the nucleons in the nucleus are also bound. These are not free particles. Okay, in 12 carbon, the nucleons are inside the carbon nucleus. And because of that, the energy that is brought in by the neutrino can go into one particle, one hole excitations of the nucleons. The nucleon can get excited, leaving a hole, they can combine. So he has gone up to 2 particle, 2 hole, and then he gets a nice agreement with the data. Okay, so that is what he shows. So similarly on the right hand side, so for both mini boon, and he will show also, this is for mini boon data, but he will also show this for Minerva data. So mini boon data is roughly around a GeV of energy. Okay, you can see that it's around a GeV of energy, and Minerva is at much lower energy, but I will just show that in the next page. Okay, so here is the Minerva and mini boon data, and I also, because Vivek was asking me this question last week, so I also put this one slide because of the Gini fit that is also there. But let me first talk about the mini boon Minerva data. So this is now 1 pi production. So the earlier one was total inclusive production, charge current, total inclusive charge current production. Okay, here total sigma. But now here we are looking at only 1 pi production in the final state. Now this 1 pi is a very complicated way. It includes any process in which 1 pion is seen in addition to whatever else is required. For example, the muon plus 1 pi. So 1 pi means not just 1 pi, but the final state lepton plus 1 pi. So you can see that, first of all, the data need not agree. The red and the blue dots need not agree because they are at different energies and they have different fluxes. As I said, the average of mini boon is at almost a GeV, and the average of Minerva is about 0.2 GeV or something like that. So they are different fluxes. They need not agree. And you can see that the theory also are different. But you can see that the Gini theory, the blue and the red lines, don't agree with the experiment also. And you can see that on the right-hand side there, you're completely off. Okay. So this is a problem here, that if you look at the details of these cross-sections, and only now the cross-sections are beginning to be taken again seriously, and more cleaner data are being made available after the 1970s and 80s. And so there is a lot of interest in actually recomputing these cross-sections, trying to understand more about them. And it turns out that, especially in these in-between energies, half an GeV and few GeV, which is what we saw in the previous slide, which will also affect ICAL data at 1 to 2 GeV, there is a lot of discrepancy between the theory and the experiment. This is a question for the audience. There is only pi naught and pi plus data, why not pi minus? Maybe I will leave this as homework. People can figure it out. I don't want to pause because we are not having much time. I will go to I think the last slide on this. So the top part is pi plus. They say pi plus, pi minus because they don't have charge sensitivity. But again, it is only pi plus data. And the bottom 2 graphs are pi naught data. In fact, the figure caption does say pi plus only, although the caption inside the figure says pi plus, pi minus, as a function of both the pion energy and the pion angle. And whichever way you look at it, you can see that more or less, especially for pi plus, you will see that the Gini data do not agree either with final state interactions or without final state interactions. Even the shape and the normalization do not agree, although it is much better for the anti-neutrino at the bottom rather than for the neutrino at the top. Okay, so there is this open question now. There is a lot of discrepancy. This discrepancy is actually so many percent. It's not 1 or 2%. 10 to 20% of discrepancy is there. And of course, I have not shown you the recent data on deep elastic scattering simply because there isn't any recent data on deep elastic scattering. So I want to make a few last words. ICAL spans the energy range just below a GeV to several GeV. Hence, it has contributions from quasi-elastic below a GeV, resonance at few GeV, and deep elastic scattering at high energy. All these processes. We must always keep in mind that whatever data we simulate has huge uncertainties because of these uncertainties in the cross sections. And we have to be very careful when we claim a result. Thank you.
Thanks, Sidhu. for a very nice interactive session. And also, I hope many of the questions that you post from time to time are kind of worked by especially the younger audience. And also, I have actually given, without asking you, I given your email typed on the chat.
Oh yeah, it was on my first page. No problem.
Yeah, I saw that. In case they need to talk to you, but so there are more questions. One on Zoom right away is Sailesh. So let me unmute him and you can answer. Yeah, please go ahead.
Yeah, hello. Am I audible?
Yeah, sure. Yeah, go ahead.
Yeah, my question is at one of the slides when you said the cross section is dependent on the energies of final states as well as the available initial energy.
Yes.
So I want to ask that won't the initial energy dictate the final energy states?
Yeah. So it's that is exactly the thing.
So why are they separate?
For example, you can see this, right? Can you see this slide?
Yeah.
So you can see that what is on the x-axis is the total neutrino energy. That's the initial energy, right?
Okay.
Because the whatever is the nucleus is at rest. This is 12 carbon, right, for this particular case. And therefore, this is the total initial energy available in GeV. Is it clear? From here, I can write the root S of the interaction and I write an invariant initial energy.
Yeah.
And you can see that the cross-section changes as the energy changes. But this is the total cross-section. Now, this total cross-section is divided or distributed into different kinds of energies of the final state, which is in the next slide. So, for example, this total cross-section, which is implicitly a function of that neutrino energy, is now also a function of the kinetic energy T of the pion. Okay, and that is why, in fact, the data for the Genie and Mini Boom don't match because the neutrino energy for the two are different. So, though it is a single differential cross-section, it depends on two quantities. Please understand the difference between differential cross-section and function of variable.
Yeah.
So this is a differential in dt pi or dp pi. It's also a function of the momentum of the pion, but it is dependent on both E nu as well as p pi. Is that clear?
Yeah.
That's all.
Thank you.
Yeah, sure.
We have another question from Bala.
Yeah.
Please go ahead, Bala. Bala Subramanian.
Hello, is it fine?
Yeah.
Ma'am, in your penultimate slide, there's something called POS. What is meant by that?
Where am I?
Sorry, POT normalized.
Oh, okay, fine. So I haven't told you many things about this slide. So first of all, CH means that it's some mineral oil. It is some object which has a lot of carbon and hydrogen chains in it. Okay. So what they have taken is that the so-called theoretical nucleus is CH. That's all. That's unit of nucleus. So instead of iron target, it's a CH target. That is the first point. And POT is the number of protons on target because these are beam experiments. Okay. So what happens is that far away from the detector, there is some beam coming from Fermilab or wherever, and then it hits a target, which is a very thin metallic layer, and that produces a lot of pions. So the number of protons hitting the target determines how many pions you get. These pions decay from pi goes to mu nu and produce the mu, which is the flux, which is the initial flux for the detector. Is it clear? Okay. Yes. So by telling you how many protons on target are there, you can tell me how many events you expect to see in the detector. That's all. That determines everything because that will tell you this thing. So if I tell you that, for example, data tells you 3 into 10 power 20 POT. Okay. So I have to just multiply by that factor to give you total value. Is it clear?
Can I comment, Indu, on this?
Sure, please. Everyone can comment.
Actually, it's not a very thin target. The target is roughly about 0.5 to 1 meter thick. And I think in Fermilab, they use, I think, a graphite or some such target. Yeah. It's pretty thick because you have to stop these protons and then whatever ions come out, they decay in a pipe, maybe about, again, a couple of meters long.
That pipe can be 0.5 kilometer long. Actually.
Yeah, that can be long. But the point is that the target is not thin, it's thick. Okay. It in fact stops the protons.
Okay, sir.
Yeah.
Okay, I see. Even I thought they were thin.
So you have a target which actually has dumped about 700 kilowatt
very thin.
power. Huh?
The Minos target is very thin. I have seen that.
No. Those are the targets in the experiment. They will be thin.
No. Minos, I mean the detector,
in the detector. No.
I'm talking about UV
that
beams.
cannot be thin because otherwise you won't produce enough particles.
My mistake. I'm sorry.
Yeah.
See, I learned something new. Thank you. Okay.
Ma'am,
No,
can I
so
ask
I would urge some of these, some of the students to go to some of these talks, facility talks which took place in Neutrino 2020. But of course, this is also there in probably now in other places, review articles and so on.
Yeah, and I will share the list of references. I'm very sorry about that. Okay.
I think there was somebody was trying to ask, same Bala you are asking?
Yeah, one more question, ma'am.
Okay, go ahead, please.
About the ICAL. Why are
I don't have a picture of ICAL, okay.
Yeah. Why, the iron ferromagnetic material alone has been chosen. Why not cobalt or nickel?
Well, cost.
Oh, okay.
Yeah,
only
detector
cost?
design is a function of many things. Okay, so.
Okay.
Yeah.
Okay, ma'am. Thank you.
Okay, so.
If you could have a permanent magnet, for example. Well, okay.
If there are any questions from YouTube, please type in quickly. And also, if there are some more questions, yeah, I do see one more from Zoom. This time from Hariom. Please go ahead.
Yeah, ma'am. This question is very basic. Like I don't know where I am doing mistake. Suppose in this there are two electrons in Baba scattering, or you can say so. These two electrons from this Coulomb force interaction, the force will be there when r tending to infinity. So I understand this cross section as the probability of interaction. So I understand this way. If this is the classical picture, I understand is this cross section should be infinite in the electromagnetic interaction, but it is not the case, right? So
no, I didn't understand your question. Why should it be infinite?
Because the classical picture is like the area, the cross sectional area of suppose there is a ball, the cross sectional area is the
correct. Yeah, correct.
Yeah, so this way the two electrons will always interact because there is always photon exchange until this at in the Coulomb force k q1 q2 over r square until r tending to infinity. So there is this cross section is infinite. I don't understand this.
Oh, no. That is not the way you look at it. Okay, fine. So I don't know how I can write anything. Okay, so the way you look at a cross section is this. A cross section is calculated theoretically by saying that I start out with a Hamiltonian, which is exact and without any interaction term. Okay, so a free particle. Let us say I have a free electron Hamiltonian at t equal to minus infinity. And therefore, I can enumerate all the states, right? I know the solutions. I can solve this Hamiltonian. I know the energy eigenvalues and the eigenstates. Okay. Now, at around t equal to 0, so you have started out with t minus infinity, around t equal to 0 and around x equal to 0. So, as a function of space and time, both, I turn on an interaction which lasts for a finite time over a finite space. This is very important. So that I again measure the state at t equal to plus infinity, and at that time that interaction has been switched off. See, there is no continuous interaction. When the particle interacts with the detector, see, this is also a very big question because the particle actually, when it interacts with the detector, that's also an interaction. But that original interaction that has happened, say neutrino electron elastic scattering or with proton scattering or whatever, that interaction has switched off by the time the final state reaches the detector and gets detected. So you're asking what is the change? So that means at t going to plus infinity, I again have the non-interacting Hamiltonian H0. So my Hamiltonian is H0 plus Hint only at t going to 0, t of the order of 0. And that switches off after that finite time interval. That's it. That is the duration of the time when the interaction is turned on. Then the scattering process happens at that time, and the final states are again free states. So the final state particle that I am going to observe is a free particle state corresponding to some free Hamiltonian, right? And that is how the whole scattering amplitude is written. That's why it's a scattering amplitude. The amplitude for the in state going to the out state because of this Hint. So you want a matrix element of this H interaction between the in and out states.
Yes.
Okay, that is what is related to the S matrix actually.
So basically, this is the small time in which they interact.
Yes, yes. So the interaction does not go on till infinity. It has to switch off at a finite time. Okay?
Okay. Okay.
Yeah. Now, the other question that you asked, it repeatedly keeps on exchanging photons, for example, right? This
Yes.
perturbative QED is called summing up term by term. So you
Yes.
can
Yes.
ask what happens if one photon exchange happens. That will give you alpha squared interaction. If two photons
Yes.
are exchanged, it gives you alpha power 4.
4.
It should
Yeah.
be
Power
much
is
smaller.
increasing.
Yeah,
Yes.
yeah. So alpha is less than 1, right? Alpha is 1
Yes.
by
Yes. Yes.
137. It's 10 power minus
137.
2. Yeah, correct. So it keeps
Yeah.
on decreasing. So the higher order terms are going to be smaller than the leading terms. And your
Yes.
perturbative
Yes.
series will converge. Now you can see in this entire talk, I have not really talked about QCD, quantum chromodynamics, because perturbative QCD is very, very difficult to achieve. So there are many, many problems with trying to understand QCD, and therefore I decided not to talk about it at all in this entire talk.
Thank you.
Okay.
So Indu, about the references, of course, there was a query. So what I was thinking is that these slides that you have,
Yeah.
at the end of the slide, you can anyway add the references as
Yeah.
it.
So
And
for
when
those
you
of you who want to know right away, the review is 1611.0770.
1611 dot
0770.
777.
Yeah, 777.
Yeah, 07770, right?
0, yeah, correct. Yeah. So this is the 2016 review. Okay, and this is by this Martini and somebody. Let me just tell you who it is by. It is Katori and Martini. So this Martini's name you already saw in the slide. So it's Martini. You can even do a search for Martini in 2016. You will find this review. Okay.
I just typed it in the chat window.
Okay, very good. Yeah. Okay.
Now, but
as I said, I could have probably done that also. And then there is a nice review of neutrino cross sections in in the particle review, PDG. Okay, you can look at that also.
Okay.
So these are the main things. After that, I'll give you some small ones, but if you, with these two, you can understand a lot of things. Okay, so.
Okay.
And I think one slide was from that graph was from Halzen and Martin's classic textbook. So.
Okay, so
Yeah.
Indu, I guess we don't have any more questions. So let me thank you for taking time and also organizing this nicely interactive lecture. And I hope it was found to be very useful. And also I hope the questions and the problems that you posed are going to be worked out by the students. And they can always, of course, many of them obviously know you, so they can interact with you even offline. So
Sure.
I would like to thank you on behalf of all the participants today. And also, before I close, I also want to make an announcement. The next talk in this series is going to be on 17th July, that is on Friday, as usual, on the same day at 6 p.m. But this time the talk is going to be a little bit different. It's not so much on science, but it's going to be about how you actually make impressive talks and presentations and so on. So the title of the talk says, "Do people listen to your talk?" And it's going to be given by Dr. Amit Roy, who is the, of course, former director of IUSC, New Delhi. So it will be a kind of a different experience and different kind of talk. So I hope you'll enjoy this particular variety. And also at the same time, it's important now for all the younger students and researchers to be also able to present their work effectively. And I think that's what he's planning to cover in this. So please come back on Friday evening at 6. So with that, I would like to close today's session once again by thanking Professor Indumathi.
So let me just say thanks to everybody for coming and listening, and stay safe. And nice to see old friends.
Thank you.
Okay. Yeah.
Thanks,
Thank you
Indu.
very much.
Yeah.
Bye.
Thanks.
Bye.